Now let's put together a quick checklist of techniques for sketching graphs of functions. We have some new techniques from calculus, the derivative tests. We want to combine those with pre-calculus techniques to get a more complete set of tools for understanding the shapes of our graphs. And remember, for us, a sketch of a graph is not intended to be accurate or to scale. It is intended to show the salient qualitative features of the functions that we're considering. And you might well ask why, in this day and age, we bother with any hand-drawn graph when you have electronic devices that can do graphing for us. These include graphing calculators and computers with graphing software. So on the subject of graphing calculators, I'll confess I don't actually own one. I don't believe I ever have owned one. Some semesters I have used one in the classroom. My experience, I found I never came across a function whose graph I could better understand with a calculator than I could by hand. Doing it by hand, knowing some calculus, is always faster in my experience. In the classroom, I found that students never became familiar enough with how to actually use the calculator to the point where it would actually offer them any true advantage. But there are computer software packages that do a very good job of graphing, and they're natural and easy to use. I do recommend these. And my personal favorite is Maple, but there are lots of others, Mathematica, etc. But actually, even with this graphing software, most of the time when I'm using it in a classroom demonstration, and not so much in my own work. For my personal and classroom use, almost exclusively, I just carry around a $10 scientific calculator, a $10 calculator. It's not because that's all I can afford, just that it's the easiest to use and the best, and get it done quickly. So let's talk about our sketching of a graph of a given function. To set up, we first of all want to look at f prime and f double prime, work them out and check, make sure that you got everything right and simplified, factor if possible. Before you get going, you'll want to think about the domain of the function and keep an eye out for what are the points of interest that you want to include. Points of inflection, maxima and minima, this kind of thing. So that's going to determine, to some extent, the scale of your graph, how big or small. You don't want it running off the page. In fact, when you get started, you're probably going to find you need to restart and get a different scale anyway. You don't have to use the same scale for x and y, by the way. In sketching the graph of a function, we want to look at certain features, including symmetry, which is a pre-calculus notion, and I'll say something about that in a moment. The other features are from calculus: intervals where the function is increasing or decreasing, and concavity, critical points, these are local extrema, also inflection points, asymptotes, and end behavior of the graph, what happens when x goes to plus or minus infinity, also intercepts if they're easy to compute. And although every example is different, not every example contains all these features. I'll try to choose a couple examples that are somewhat representative, and we'll work through their graphs during our time together here. Since the whole point is to show you something that can be realistically sketched by hand, I'm going to switch from the computer to handwriting for that demonstration. But first, let's talk about symmetry. As I promised, we want to recall what's meant by an even function. It's one whose function satisfies f of minus x is f of x. An example is the cosine function. That's evident that it's even from the fact that if you reflect the graph in the y-axis, the graph stays unchanged. Every point on the left side reflects back to the right side. This is what an even function looks like. Other even functions include polynomials in which every term has even exponent. Not just even degree, but every exponent is even. Let's look at an odd function. That's a function that satisfies f of minus x is minus f of x. So the minus just comes out. An example of that is the sine function. You can tell graphically that it's odd by the fact that if you turn the graph 180 degrees around the origin, you get the same graph back. Other examples of odd functions would be polynomials in which every exponent is odd. Now there are other kinds of symmetry than just evenness and oddness. For example, both the sine and cosine functions have translational symmetry. If you shift the graph left or right by 2 pi units, the graph again stays unchanged. But most functions have no symmetry at all in their graph. Most functions are neither even nor odd or anything. So symmetry is not something that can be incorporated in all cases, but if you have symmetry, it will cut down your work, because whatever you do on one half of the graph will translate into the other half. Now we're ready to do some examples. Let's look at this rational function, x squared plus 36 over 2x. You'll notice that this is an odd function. If you plug in minus x, you'll get out a minus. The top is even and the bottom's odd. That makes the whole thing odd. So f is odd, and that will help us in the shape of our graph. We can check that the right-hand side flipped upside down becomes the left-hand side. Let's do the derivatives by the quotient rule. Now we identify the critical points. We have 0 and plus or minus 6. Notice the critical points where the derivative is either 0, plus or minus 6, or undefined, and that's at x equals 0. I'll mark the critical points on an x-axis. None of these functions are defined at 0. It's going to give me a vertical asymptote. I know that from looking at the function. That is going to go up to plus infinity on the right, down to minus infinity on the left. As a vertical asymptote, nothing's defined there. For x bigger than 6, positive, positive, positive. Between plus or minus 6, positive, negative, positive, makes negative. And here as well, same reason. For x less than negative 6, negative, negative, positive, makes positive. For x positive, f double prime is positive. For x negative, f double prime is negative. That gives me the shape of the function on each of these 4 intervals. We get all 4 possible combinations arising. Let me go ahead and write out the intervals where f is increasing and decreasing based on this information. Note that although f is decreasing from minus 6 to 0 and decreasing from 0 to 6, it is not decreasing from minus 6 to 6. You can't include the point 0. That's where f is not even defined. Let's go ahead and start the graph. I'll indicate our points of interest. I'll fill in the values of the function at those points. I have 6, 6, minus 6, minus 6. On this interval it's decreasing, increasing, concave up, increasing concave down, decreasing concave down. Notice here that 6, 6 is the, as in unique, local minimum. Minus 6 is the unique local maximum. So here it increases, then decreases, so that's a local maximum. Decreases and increases, so that's a local minimum. Let's look at end behavior. As x goes to infinity, you know from laws of limits that this goes to infinity. those two limits are infinite, so that tells you a couple things. First of all, there are no horizontal asymptotes. Also, there's no absolute maximum or minimum. Not only that, it has no inflection points. Notice that although it switches from concave down on the left side to concave up on the right side, there's no inflection point here. The point 0, as x equals 0, does not even give a point on the graph. We have a vertical asymptote. So you check by these limits. Limit as you approach 0 from the right. Again, from elementary consideration of limits. And on the other side, so the y-axis, x equals 0, the line x equals 0, is a vertical asymptote, the only one. Having drawn the graph, I should remark on the symmetry. So this thing, if you turn it around upside down to the other side, 180 degree turn around the origin, you'll see that this exactly matches up with this, and that's coming from the fact that f is odd. Now there's just one other feature that I will point out, and it's not everybody that really cares to look at these things, but there is another asymptote. It's neither horizontal nor vertical, and it's this line, which goes through the origin with slope a half. So line y equals 1/2 x. So y equals 1/2 x is an oblique asymptote, meaning an asymptote that is neither horizontal nor vertical. So an asymptote is just a line that the curve approaches asymptotically. And you can see that this is an oblique asymptote from rewriting this. It's x over 2 plus 18 over x. And if you see what happens when x goes to infinity, this term tapers away, and asymptotically this function looks a lot like just x over 2, and the same in the other direction as x goes to minus infinity. So in both the far right and the far left directions, the curve is approaching this line. It's an asymptote.